Right? So if you only have 4 peaks, and you have a lot of hydrogens, right? Less peaks, more hydrogens, think symmetry. So we should be thinking symmetry right away. Which one of these proton peaks should we start with, do you think?
The singlets.
Which one do you want?
The 6 singlets.
The 6 singlet S, right? So we'll start here. So we have a peak at 1.17. That's for 6 H's, that's a singlet. So how many nearest neighbors does it have?
None.
None. Right? The other thing I like to do, label these A, B, C, and D. Okay. Actually, I don't know if I would start with that one. This one might be kind of tough to start with. We'll start with
Because you
the,
need 6 hydrogen.
we'll start with the easiest one.
Well,
How do you
the
decide which one to start with?
You gotta pick one.
C
Go.
has to be an OH probably, huh?
All right, so let's look at C. Who knows what this D2O thing means?
Deuterium.
So deuterium. Is deuterium NMR active? Is D NMR active?
No.
So if I have a peak that's an OH or an NH, and I put it in D2O and I shake it, right, that peak's going to disappear because I'm going to go from a OH, right, to a OD, right? So I won't see that, right? The protons can exchange, right? It's like an acid-base reaction. If you do that, it's a good indication that you have either an NH or an OH there. So this tells us what? What do you think? It's a broad peak. It disappears after a D2O shake. It's worth 1 hydrogen. What does that tell us?
I'm sorry about that. But would you also get water then?
Yeah, you get water too.
But like, would you have a water molecule in
You have a water peak then too. Yes, in your spectrum.
Okay.
Yep. So C is telling us we have an OH, right? Squiggly lines. I don't know what's bonded to that oxygen still. Right? I don't know what's bonded to that oxygen. Okay.
How you don't? Oh, no.
Don't know. What about, let's also look at, so that's C. Let's look at our Hertz. If they have the same coupling constant, what does that mean?
They split each other?
They're splitting each other, right? They're next to each other. So that means proton D and A are next to each other. They're splitting each other. They have to be next to each other. So let's see. Proton D is only 1 proton, right? So H, D. How many nearest neighbors does D have, though?
6.
Has to have 6, right? What's the easiest way for it to have 6 nearest neighbors?
2 methyls?
Probably be these would be protons A. Do we know what's bonded to this other carbon yet? No, we do not. Squiggly line. So let's check, make sure we did this right. So what was the splitting of A? HA up there was what? A doublets. How many nearest neighbors does it need to have?
1.
How many nearest neighbors do we draw for HA? So that's good. HD needs to be a septet. How many nearest neighbors did it need to have? 6, right? And it has 6. They're both coupled to each other, so that makes sense. We check off A and D. All right, so probably the strategy, these strategies to do is, if you have a coupling constant, do those protons first sometimes, so you know they're next to each other, right? So now we have 2 pieces. One thing I haven't been doing, that I normally do a better job of. You have them like your formula. A lot of people ask, how do I keep track? Right? Well, we know we have an OH piece, right? So let's subtract out an OH. We have C6, H13, There's no more oxygens left, right? What other piece we just get? We got a C3H, what, 7? There you go. C3H6. So that's what we have left. We have left is C3H6. And the only peak we have left is 6 H's for a singlet. So what does that tell you? What kind of carbon do we also must we have here?
Carbon with no hydrogens.
We also must have a carbon that's bonded to no other hydrogens, right? We have to have a carbon that's bonded to no other, not bonded to any hydrogens, right? Because we're left with C3H6, right? So it's probably going to be 2 other CH3s, and they have to be singlets with no nearest neighbors. Okay, so let's draw those in. These will all have to be HB, right? Can there be any hydrogens bonded to this carbon?
It's already got one.
No. Well, I don't know what they are yet, right? So we have to make sure these are still singlets, so they can't be any hydrogens. So we can even write here, no neighbors. Right, no neighbors for HB. So now do we satisfy, subtract out C3H6? Right, so these, now we have all the pieces. Now we got to put them together, right? We have all the pieces, now we got to put them together, yep.
When I was doing this, I was looking at like the 1.17 and the 1.65, and like in that area in our chart, it's allelic, so it has double bonds. How do you like? How do you
know?
Right, like how can you not look at that?
Yeah, so be careful. So you know your area, you know your regions, right? And you say 1.65, it has to be an allelic double bond. But if you don't have any pi bonds, can you have one?
Right.
No. So your regions are just, right, there are guidelines. They're a starting point, but they're not going to tell you the whole story, right? So I think looking at your frequencies later on might be, right now we should look at our frequencies. Right now that we've figured out our pieces, now we should go back and look at our frequencies, because we can say to ourselves, well, oxygen, is oxygen going to make things shielded or de-shielded? So maybe we want to put something, right, that's a little farther downfield next to that oxygen, right? Yeah. Okay. But if something's bonded next to the oxygen, it's going to be even farther downfield. So how do we want to put this together? How should we put this all together?
Connected to this.
Does it matter which one's connected to which one of those carbon bonds?
This carbon needs 2 bonds,
Yeah.
right? So essentially we need to put these 2 groups on here somehow, right?
Mm-hmm.
Everybody see that? Does it matter which way we put them on? No, it actually doesn't. So let's go ahead and put these on. So let me erase this. Everybody see this carbon needs 2 bonds. We have 2 pieces left. And if we're saying it doesn't matter which one goes where, let's put the OH here. That's OC. Let's put oops. Don't add. That's right. It's not going to look the prettiest, but that's okay. Alright. This is D, A, 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 A. See how you put that together? Does everybody see how I pieced it together at this point, at least? But now we stop, right? Because now we got to check our work. All right, we got to make sure the molecule we made matches up with the data we have. Right? We want to make sure the molecule we made matches up with the data we have. So So let's go back and look. So A is at 0.91. With 6 hydrogens, it needs to be a doublet. So let's find HA. HA, 1, 2, 3, 4, 5, 6. That's good. How many nearest neighbors does it need to have if this is going to be a doublet? How many?
1.
1. So it has 1. D, how many protons for HD? 1. It's going to be a septet. How many nearest neighbors does it need to have? 6. Does it have 6 nearest neighbors? 1, 2, 3, 4, 5, 6. It does. They're both coupled to each other. That's good. Coupling constants match. HB. HB needs to be a 6H singlet. Here's HB. 1, 2, 3, 4, 5, 6. We have 6 protons. That's good. Does it have any nearest neighbors? No, so that's good. It should be a singlet. And the final one is HC. And HC is a singlet. 1H. It's broad. It disappears. It's probably an OH. So this is the process you have to do to do these problems. The first thing you got to do is degrees on saturation. Notice I didn't even actually use these. I mean, I could have. It doesn't. Right, does this molecule have 4 different types of carbons? That's another good thing to check, right? 1, 2, 3, 4. Always go back and check the data. Make sure it matches whatever you made. So on a test, right, what do? First thing, you do degrees on saturation. All right? And you write down, I want you to write this down. If you don't write anything down, I will absolutely promise you that you'll get enough points. Right? Show your work. I will give you credit for showing your work. I want to see how you think, right? It's not just about getting the right answer, it's about how you think about it, okay? Degrees on saturation. Have your molecular formula out. Start building your pieces in based on the splittings, right? Subtract out. Make sure you don't lose any protons, carbons, or oxygens or nitrogens. Get your pieces. Get the splitting right. Once you get the pieces, put them together. Then check to make sure it matches the data. Right? Check to make sure it matches the data. Okay? Any questions on this? Promise.
For Hasty, I was thinking the chemical shift should be a little bit down here. Because it's close to oxygen.
Yep, so OHs and NHs can kind of appear wherever they want to. There's no necessary rhyme or reason to where OHs and NHs end up at the spectrum. That's why they told you this, right? Because of the chemical shift, it wasn't clear that it was next to the OH. Right? You'd expect it to be much more downfield, right? So they tell you this thing about the D2O to let you know this is an OH. Good question. Yes?
Can we do the one that gives you just the mass spec?
The 180, 182 one?
No.
No?
Can we do the molecular mass of 71?
Okay. So are we okay with this? No?
We're
Yep.
going to have to know the degrees of unsaturation formula.
I'll give it to you. Yep. I promise everyone that you guys have to know formulas. So I'll give you the degrees on saturation formula. Just like the one I emailed to you. Right? Does everybody understand what X is though? Okay. Yeah, because if you mess, the thing is, it's silly. If you mess this up, you really can't do the problem. Right? It makes it a lot harder. It'll never be a half. Right? It'll always be whole integers. Right? You can't have half a degree of unsaturation. Right? You can't have half a ring or half a pi bond. So it always should be whole integers. Yep.
Can you not know that it's saturated by the CNH n plus 2?
Yeah, there's a way you can do that too with the regular formula. But this is, yeah. It just do this. Tita.
Is there going to be like, what does a 2 and a 3 mean?
So 2 or 3 would mean what? So right here, let's look at this molecule right here. How many degrees of unsaturation do I have here?
1.
Everybody see this? How many degrees of unsaturation do I have?
4.
I have 1, 2, 3 pi bonds and a ring